Usually we learn, F equal to gmm over r squared, right? I can get rid of that because that's unnecessary and actually hiding the essence. Why?
Said mass is not important.
Say it again?
We say that mass is not important.
Right. So what should I have instead?
But you can't say if your mass is zero because
No, my source mass is not zero.
yeah, no,
Particle mass.
the particle mass
Right.
because it's like multiplying by.
Okay. Yes, but we can do without the mass altogether. We define an acceleration equals to gmm over r squared divided by m, assuming that the inertial mass is the same as the passive gravitational mass and so on. They cancel out, and you end up with acceleration. Is we're going to define an acceleration field outside this mass. At every point outside this mass, there is a specific number with a direction, right? I'm going to forget about the direction because it's obvious. I'm just going to talk about the number. It's spherically symmetric, right? At every point in space, there is a specific number telling you what the acceleration is. If you have particles moving with all kinds of different velocities in different directions, every single one will have exactly the same acceleration at this point. Correct? Is that true about any other force? Can you do this with any other force? No. Because what you have for other forces is exactly that, a force. You don't have an acceleration, you have a force. To find out the acceleration, you might need the mass-charge ratio and all kinds of other things. It might be velocity-dependent, etc. Only for gravity. So for gravity, we can define an acceleration field. Which, right away, even if we didn't do anything more, that's a beautiful idea. Okay? And it makes it very intuitive that all these particles will have exactly the same acceleration. Now, before we saw, what is acceleration from the space-time perspective? It's equal to
Curvature.
world line curvature. So we can, if we want, talk about a world line curvature field. We didn't gain anything, it's just kind of a nice idea. At every point outside this mass, there's a world line curvature field. So we have the gravitational force, and usually, at least in high school, you say F is equal to gmm over r squared and so on, right? But what makes a lot more sense is to talk about the acceleration, because the acceleration of all particles is the same. So you could imagine an acceleration field outside of mass. Here's the Earth. Outside the Earth, at any point, we can compute what the acceleration would be of any object, whatever size, whatever shape and mass, etc., density. We know exactly what the acceleration would be. Acceleration would be such and such amount in that direction. Over here it would be the same amount, but in that direction. Over here it would be a little bit less, and so on and so forth. So instead of talking about a force, and then having to figure out how that force affects different particles, what we do is we talk about an acceleration, a field in space, and the acceleration that any particle will experience in that field. So gravity has exactly that feature, which is the equivalence principle, that all masses accelerate in the same way. When they come into a certain region of space, they all accelerate. Now, depending on their initial conditions, their direction and speed, their acceleration is added on to the velocity and takes them in a different trajectory and so on. But at any given point in space where there's a gravitational field, there's a unique acceleration pointing in some direction, and it doesn't really matter how the particles are moving with whatever speed, they all have this acceleration at this point in space. Okay, we have, let's say, a spherically symmetric mass, and over here, spherically symmetric mass, and we have outside here a force gmm over r squared. Now, of course, as a result of the equivalence principle, we can write acceleration divided by the mass, and we get gm over r squared, which means that at every point in space outside this mass, we have a radially directed acceleration with an amount equal to gm over r squared at every point. Now, this is very nice because what that means is that we have an acceleration field. And this is something that can only be done in gravity. If you're having, for example, an electric field or any other kind of field, you have to use F, the force field, because the resulting acceleration of this force, let's say it's a QQ over r squared force, the resulting acceleration will be QQ over r squared divided by m, force over mass. So you're going to have to talk about a force field. If you're talking about gravity, you can uniquely define an acceleration field rather than a force field. So gravity produces an acceleration field. What that means is that at any point in space, at a given time, you have a bunch of particles. You have a particle moving with a velocity in this direction with a certain speed. Another one is moving like that. Another one is moving like that. Whatever. As they cross this point, if they're crossing here simultaneously, let's say, if it's a static field, it doesn't matter, then they all experience exactly the same acceleration, irrespective of their mass and irrespective of their initial conditions, their speed and direction. And that's why you can uniquely define at each point in space the acceleration field. And we don't really care in terms of basic physics about the initial speeds and directions of some particles. Those are like particular examples to solve later. The theory is built on the fact that you have a field in the space around this spherically symmetric object, and it's an acceleration field given by this. So think of spherically symmetric mass, which means that not only the geometrical shape of it, but the density is also spherically symmetric. So you all know that you can consider all the mass as though it's concentrated at a point at the distance of right from the center. Now, at each point outside, I have a certain force, mm over r squared, right? Again, I'm forgetting out the g and the minus and so on, it's not important. I have mm over r squared, and then I have the resulting acceleration, which is just m over r squared. So really, there's no need for me to talk about the forces. I just talk about the acceleration. I can now consider that there's an acceleration field outside the mass, given by m over r squared. At every point in space outside the mass, there's a field, meaning that should a particle enter there, it will pick up that amount of acceleration. And amazingly, it doesn't depend on which direction the particle is moving or how fast, right? If it's moving this way, if here's the mass, and the source mass, and there's a particle moving this way with a certain speed, and there's another particle moving this way with a different speed, and one moving like this with a different trajectory and speed, at the point where they all meet, what accelerations do each one have? M over r squared, in the same direction towards the center. Does not depend on anything else. So it's really an acceleration field. Of course, how it affects the particle's trajectory depends, obviously, on the initial conditions. If it's coming like this, it has acceleration like this, it'll bend like that. If it's going like this, it has acceleration like, right? But the acceleration itself, which is the important thing, if we're talking about the physical phenomena, we want to know what is the effect of the source. The effect is to give any particle an acceleration. Different particles with different speeds and different directions, that's already specifics. That's not part of the theory. Right? That's when you have a particular situation, you use the theory to solve that. So we have a very beautiful thing. Gravity is represented as an acceleration field. It's not like QV cross whatever, and you don't need the charge of the particle, you don't need the mass of the particle, you don't even need the velocity of the particle. At every point, there's a specific acceleration. It's a vector, but we can kind of ignore the vector aspect of it because it's only a radial vector. If you're using spherical polar coordinates, you have one component, though mostly like what I'm going to do is talk about the r component of A, AR, not as a vector, but always keeping in mind that it's 1 out of 3. So at every point you have gm over r squared, and what that tells you is not something that you then have to compute what the effect is. This is the actual effect. Any particle, if there are 10 different particles here with different masses going with different speeds in different directions, they all, without exception, have exactly the same acceleration in the same direction. So you really have a property of the space or the space-time around this Earth. And that gives you a real sense that it has something to do with space, or if it's over time, space-time.